Imagine, for a moment, the atom. For over a century, we've pictured it as a miniature solar system, a dense nucleus at the center, with tiny electrons orbiting it like planets. This elegant image, proposed by Ernest Rutherford, was a revolutionary leap forward. But it had a fatal flaw, a secret that threatened to unravel everything. According to the laws of classical physics, an orbiting electron, being a charged particle in motion, should continuously radiate energy. This loss of energy would send it spiraling inward, crashing into the nucleus in less than a nanosecond. If this were true, every atom in the universe should have collapsed long ago. The screen you're watching, the air you're breathing, you yourself, none of it should exist. The stability of matter was a profound mystery. Into this crisis stepped a young Dane, a brilliant and visionary physicist named Niels Bohr. Arriving in Manchester in 1912 to work alongside Rutherford, he was determined to solve the puzzle of the unstable atom and save reality from its own paradox. Bohr's genius was not just in seeing the problem, but in daring to look for a solution in the most unexpected of places. He took Rutherford's planetary model and combined it with a radical new idea from the German physicist, Max Planck, quantum theory. The result was a stunning breakthrough, a new picture of the atom that changed science forever. In Bohr's model, electrons don't just orbit anywhere. They are restricted to specific, fixed paths, like trains on a track. These were stable energy shells. An electron could exist in one shell indefinitely, without losing energy and spiraling to its doom. But the truly revolutionary idea was what happened when an electron moved between these shells. It didn't travel through the space in between. It simply vanished from one orbit and instantly reappeared in another. This was the quantum leap. And when an electron leaped from a higher, more energetic shell to a lower one, it released the excess energy not as a continuous wave, but as a single, discrete packet of light, a photon. This beautifully explained why different elements, when heated, glow with their own unique, signature colors, their atomic fingerprints. This new quantum world was bizarre, and its implications were deeply unsettling. Bohr wrestled with its strangeness, eventually proposing his principle of complementarity. He argued that at the subatomic level, things could possess contradictory properties. An electron, for example, could behave as a solid, definite particle in one experiment and as a spread-out ethereal wave in another. You could observe one aspect or the other, but never both at the same time. This idea of an inherent uncertainty and duality at the heart of reality sparked one of the greatest debates in the history of science. On one side was Bohr, the champion of the new quantum weirdness. On the other was his dear friend and intellectual sparring partner, Albert Einstein. Einstein, who believed in a clockwork universe governed by clear, predictable laws, could not accept this randomness. God, he famously declared, does not play dice. Bohr's legendary reply captured the essence of their disagreement. Einstein, stop telling God what to do. It was a clash of titans over the very nature of existence. As the world plunged into the darkness of the Second World War, Bohr's life took a dramatic turn. After Germany occupied Denmark, Bohr, whose mother was Jewish, became a target. In 1943, he made a perilous escape, smuggled to Sweden in a fishing boat. From there, he was flown to Britain and eventually to the United States, where he was drawn into the top-secret Manhattan Project. Yet, as he witnessed the monumental effort to build an atomic bomb, he grew deeply horrified. He understood, more than almost anyone, the terrifying destructive power that was about to be unleashed. After the war, Bohr transformed from a revolutionary physicist into a global statesman for peace. He tirelessly advocated for an open world, urging nations to share scientific knowledge and establish international control over nuclear weapons to prevent an arms race. He became the philosophical conscience of the atomic age he had helped to create. Niels Bohr not only gave us our modern picture of the atom, but he also spent his life grappling with its profound consequences, reminding humanity that with great knowledge comes the greatest responsibility.